Good evening, everyone, and welcome all of you for this week 11 live session for the Smart Grid Basics to Advanced Technologies NPTEL course by Professor N.P. Padhy and Professor Premalata Jena. And I am one of the TAs for this live session. My name is Gagan Meena, and I am a fourth year PhD student at IIT Bombay in Power Electronics and Power System Engineering specialization. Let us start today's session. So this will be the agenda which will be following for this live session. We will be going through an overview of week 11 material, which was there in the class recorded sessions. And then we will discuss certain questions. We will also take certain questions, certain topics related to those questions to dive deep into those topics when required. And if you have any doubt, you can ask in between as well as after the class. Just to remind you, these are the deadlines for submitting assignment 11th and assignment 12th. Deadline for assignment 11th is Wednesday 9th April, and for assignment 12th is 16th April. And that will be we'll be having the last session next week on Monday, and one TA will be having last session on Tuesday. So you can attend both of them, or as per your availability, you can attend. And by the way, all the slides, recordings of these live sessions, as well as the PPTs used during these sessions are all available in the Google Drive link, which is available on in the problem solving sessions tab on the portal. You can go through them, and if you have any doubt, you can post in the discussion forum, or you can even mail us. So this is the link for the URL for the recordings of the live sessions, which for the session which is happening every Monday 6 to 8. Okay. We'll begin with the overview of week 11. I have already told in the previous sessions as well that beginning from the week 9th onwards, all these contents are based on demonstration. Whatever we have learned till now, till week 8, is being implemented. Either on a simulation platform or hardware, or even both. So going through these last 4 weeks, you'll get an idea how we can actually implement these learnings, concepts which we have gone through in 8 weeks, how to practically implement them. And once we do it on simulation and we are able to verify the results which which are as per our understanding or concepts which we have learned, then we are confident that the simulation will also run on the actual hardware. Once the simulation is done, we go for the hardware platform or the test bench which we have. We do different types of simulations, real-time simulations using hardware such as hardware in loop and this hardware in loop simulations. We will see what are the hardware in loop simulations and what are the different types of hardware in loop simulations. That's why starting with the theoretical concept, once we know or we have developed certain control algorithm, we need to ensure that it works as per the intended requirement before actually implementing it on a particular system. And because it's very important, the system might be of critical importance. That might be a critical system, such as power system or power grid. Power grid is a critical infrastructure, and so is the what we can say is communication or not. Okay, sometimes of certain types of communications, or you can say surgery, which are being done by the surgeons in the operation theater who are now using these different robots. All are controlled via algorithms and different controllers, logics which have been implemented in their software. Everything is running behind. So, so before actual implementations, lot of trials are done, simulations are done, hardwares, prototypes are made, and then finally a product is made, and that is also run through several trials so that uh, there is no error. Let's say there is, or even if there is some error, it is manageable. If a robot goes wrong, there is an option to manually control it. The surgeon can take over it. It's not that the robot will be independently doing the surgery. It is aiding the surgeon to do the surgery in less time as well as with precision, and yeah, it helps the doctors can oversee the surgery, and they can, and in that way they can even supervise more number of surgeries at a time, unlike those earlier days when they had to be present in each and every surgery. But now they can supervise these surgeries. As that surgery will be done in less time, they can move on to the next surgery. That's why once an algorithm is made, we need to verify that on simulation as well as on the hardware platform. The same thing we are doing here in week 9 onwards. Whatever concepts we have learned, we are trying to replicate them, the results derived, the logics which were made, and their intended output which we were expecting. We want to verify them via simulations as well as then doing it on a real prototype. Because power system is a critical infrastructure, we cannot directly go and connect everything to the system without testing it. It might result in, can have adverse impact on the operation of power system and ultimately leading to reliability issues. Security and reliable operation of our system is a very important, is of prime importance. That's why we want to ensure all the checks and balances before we are integrating any sort of equipment into the system. That's why detailed procedures are there, detailed standards are there. That's why we have studied standards in the first week, where we studied smart grid standards. These standards are very important to ensure reliable operation of power system, to ensure security, to ensure uniformity also. And when uniformity is there, and it's easy to adopt everywhere. Economies of scale and everything is there. The standards are very important, specifications and then rules, regulations, grid codes, all these need to be followed. That's why there are a lot of so many tests or conformance practices are there. Procedures are there before for integrating any equipment. You can take another example. These autonomous vehicles, they are fully driven by sensors. They take input different. So many cameras are there. So many sensors. Lidar sensor is there. The proximity sensors are there. Different types of sensors are there which take a lot of data, and they will do different stuffs, do analysis, and based upon the algorithm logic with which they have been trained, these vehicles would work in tandem with that. They're supposed to work in tandem, but there are so many things which the vehicle is not trained for. Not each and every possibility has been covered in the training data which these machine learning algorithms are using. That's why so much testing goes into everything. Okay, in this 11th week, the demonstration was the topics which were covered were energy management of TC microgrid, design of smart grid and practical smart grid, and a case study for it. Then system analysis of AC/DC smart grid, where you talked about the AC/DC power flow, how it would undergo a change when we move from transmission system to distribution system because of the increasing R/X ratio in the distribution system, and the techniques hitherto which we have been using for analysis and transmission system were Newton-Raphson and fast decouple, but we cannot make such assumptions as we were able to make in fast decoupled power flow because of the high X by R ratio in transmission system. We were able to decouple the equations, and we were able to say that P is directly proportional to theta and V is directly proportional to Q is directly proportional to V. But such kind of a decoupling this assumption of decoupling doesn't hold true for distribution system of. Moreover, in transmission system, we were assuming because on transmission system, all the three phases are nearly, the voltages are nearly 1 per unit. So we take that assumption that we do the analysis on a per phase basis, at least for steady state analysis, we can do per phase basis. And then we know that voltages are apart 120 degree apart from each other. Doing per phase analysis was sufficient. But here in distribution system, which is inherently unbalanced, per phase analysis is cannot be done. We need to do full three-phase analysis. Further in distribution system, so many components are there. Distribution system has much more, many more number of lines, many more number of consumers, many more numbers of components, and all of those components need to be modeled in detail. Their detailed modeling is required to capture their behavior. Now, because of increasing penetration of distributed generations in the distribution system, their inverter control the mode of operation of DG inverter control needs to be modeled. All these things are required, and this makes the distribution system power flow analysis little more involved, you can say. That's why we have different types of new power flow algorithms for distribution system. One of them is forward backward sweep. Then another one is forward backward sweep. Then one is direct power flow. What they call it, direct load flow. Then implicit Gauss. So many more algorithms are there which can be used for the distribution system power flow analysis. Okay, we will move ahead. We will take up this topic again when we go into the system analysis of AC/DC smart grid. Now moving on to the energy management of DC microgrid. We had talked about demand response and demand side management for the distribution system as a whole, where we would want to, the utility would always want to have a flat load profile, right? If the load profile is something like this, experiencing two peaks, we can say one is morning peak and then an evening peak. I would say one peak here, then lean, then another evening peak, and so on, like this. The utility would always want to have this would be the ideal load profile, load or demand profile. And to track this type of demand profile is also very easy because generation profile will also be set. We would easily know that so much generation is required, and we can have easily keep some buffer of 10 to 15% to uh, to account for post and planned outages. To ensure reliability, to have a high reliability. We can ensure that, right? It's very easy, but it's not so easy. And the load profile is something like this, and this is also not so smooth. It's keep on, and there are so many jitters there, and the generation needs to track this demand. And you can easily see that the difference between the peak and the the highest and the smallest demand is quite huge. This is the base generation which we require all the time, and above that we need to, or we can say, let's say this one. To say this is 9, this is 1 to 24 hours, and let's say this duration is 4 hours. We need to keep this much additional generation just operating it for 4 hours, and rest of the day this generation will not be used, and this will repeat every day. Not exactly, but still we can see a big amount of generation is being utilized only for 4 hours a day. Its utilization factor is very, very poor, and this makes the operation inefficient. That's why the utility wants the load profile, demand profile to be as close as this flat profile. And for this, we want this peak to shift here. We have seen the peak shifting and valley filling. So this is peak shifting. We are shifting it here. And if we increase some load here, this will also go up. And this will also go up. So by manipulating the demand, by giving some incentives to the consumers, or the utility can have contracts with the consumer for interruptible loads. They can have agreement with them that they would incentivize them if they are ready to give the control of their equipments to the utility. And whenever they want, they can control their equipment within a desired, within the permissible uh, band which is being agreed in the contract. For example, the AC which is there, the AC, the air conditioning system which is operating in the malls, big commercial complexes. If we increase the temperature of the AC just by 1 degree, just by 1 degree, if we increase the temperature, that would not at all affect the comfort level of the customers which are there in the complex. But that would have a huge implication in terms of the electricity bill. 1 degree increase in temperature would reduce the electricity bill significantly. That's why such kind of uh, thing which we have already seen for the existing distribution system. Here we are talking about the energy management of DC microgrid. Let us move into that. Let me share the screen again. Just a minute. Okay. I'm sharing the screen again. Hope this time it's going to be there in the full screen mode. And also I'll be able to control the slides here. Good. Now moving on to the energy management of DC microgrid. Here for managing the energy, we discussed about the power flow control strategy for the energy management and what are the features of the power control strategies. The power control strategy, a good power flow control strategy can help us reduce the peak demand, which we have seen in the previous that graph, right? The utility wants to have a flat load profile. One of the features of the power flow control strategy would be to have ensure to have a reduced peak demand, to have a smooth transition between different modes. And I hope all of you remember these modes, right? Very easy, grid connected mode. Then isolated or islanded. And then one is transition mode. And we have already seen three types of microgrid, right? DC microgrid, AC microgrid, and hybrid AC DC microgrid. Effective control, and yes, a good power flow control strategy would result in effective control and energy management. It will also reduce stress on the battery. That means it will avoid frequent charging and discharging. Avoid overcharging and deep discharging. And all this, when we reduce the stress on the battery, it's increased. It's the result will be increased life of the battery. And then it will cover grid connected and islanded mode. Yeah, smooth transition is there, so it will cover. Already captured it there itself. And UPF feeding to and drawing from the conventional grid. It will also ensure that the power flow between conventional grid and microgrid happens at UPF, unit to power factor. Right? Now we will see this power flow control strategy. Here in the DC microgrid, there are three modes which are listed here. Actually, there are two modes which are divided into three. This is actually like this. This is grid connected. And then this is isolated. Even in isolated also, we can have these two modes. Let us see what this power flow control strategy says. We are starting here. First thing which we need to check is whether the grid is available or not. If grid is not available, then we need to check whether the generation from the solar PV panel is more than the load or not. Is PV greater than load? Yes or no? If no, that means we need to have battery discharging to meet the load. We will check whether the SOC, we will check the storage, how much is the energy content in the storage. Is SOC less than 30%? No. Then battery will supply and PV will act at, PV will provide maximum power because load is more, and the battery will supply the load. We are checking here. If the PV is more than the load, if the PV is more than the load, then we are checking. If uh, the power from the solar panel is more than the load, yes or no. If it is no, that means the load is more than the PV panel. And that's why the power from the solar panel is not sufficient to meet the load. Therefore, we need to discharge the battery. We go here because the load is more, we need power from the battery. And now we need to check whether the storage is what's the status of the storage, what's the SOC of the storage. If the energy stored in the storage is less than 30%, then we need to go to A. And if it is no, SOC is more than 30%, that means we can discharge the storage. The PV panel will act at its maximum power. It will be supplying the maximum power. It will be operating in the maximum power mode, and the load, and together with the battery, it will supply the full load. But if the storage, if the associate the energy stored in the storage is less than 30%, then we need to curtail certain loads. And the logic is given here. Similar logic we have already seen in the previous week also. Now we'll check how much is the SOC of the storage. If SOC of the storage is between 30 and 20%. Okay, SOC is between it is between 20 and 30%. Then the battery will supply, PV will operate at MPPT, and battery will supply essential and non-essential load, both. Okay. There are two loads. One is essential and one is non-essential load. Now, if the SOC is between 10 and 20, then only essential load will be supplied and PV will act as MPPT. But if the SOC goes less than 10%, then no load. Load is curtailed. The battery will not be able to supply the cater to the load. And in this case, the PV or the battery will act as the in the bus regulation mode. And no load will be supplied. Okay, this is captured here. Now we were here. The SOC was less than 30%. But if your SOC is more than 30%, then the PV will act as MP at maximum power point and the battery will supply the load. Okay. If here we were in this case when the load was more than the PV. Now if the PV is more than the load, then we need to check. So the generation from the PV panel is more than the load. We need to check the status of the storage. If the storage is already at 90% SOC, we cannot charge the storage further. Then the PV has to operate at off MPPT, right? And the battery will be idle or disconnected. The PV will act at off MPPT, load will be supplied, and the battery will be disconnected. It will not be charged. But if SOC is less than 90%, then the PV will will keep on operating at maximum power point, supplying the load, and excess generation will be used to charge the battery. So here battery is absorbing. Here battery is absorbing or charging. and PV is at maximum power point. Okay, we have reached up to here. Okay. This was for the isolated case when the grid was not available. Okay, now grid is available, yes. If grid is available, then we are checking two things, whether it's a peak hour or off peak hour. If it is not a peak hour, we go to C. We go here. It is not a peak hour. Now we again check what is the status between the PV and load. Is PV greater than the load? Yes. Generation is more than the load. Then we need to check the status of the storage. Is the SOC more than 90%? Yes. Then what will happen? The PV will generate excess. PV will operate at a maximum power point and the excess generation will be given back into the grid. The grid will be absorbing here. Battery will be ideal because it is already fully charged up to 90%. We cannot charge the battery more than 90%. That will result in overcharging, and we want to avoid overcharging and deep discharging. We have already discussed here. We want to reduce the stress on the battery, and for that we need to avoid overcharging and any kind of deep discharging. That is very important to have increased lifespan of the energy storage. That's why if the SOC is more than 90%, then we will not charge the battery. Battery will be idle, and the excess generation from the PV will go into the grid, and grid will be absorbing. PV will be acting at a maximum power point. Load will be supplied. Battery is disconnected, and grid is absorbing. If SOC is less than 90%, then what will happen? Excess generation from the PV, which is operating at maximum power point, will go into charging the battery. And grid will remain idle or disconnected. No need to take supply from the grid. The PV generation is sufficient to meet the load as well as to charge the battery. Now, if the PV generation is less than the load, then what is then we need to check SOC. If the SOC is sufficient to supply the battery, we will supply the load. Otherwise, we will take it from the grid. So if SOC, now let us see, SOC less than 60%, SOC, if SOC is more than 60%, which is this case, then what we will do, we will not take anything from the grid because this is not a peak hour. And battery is sufficient. If battery has sufficient storage, battery can supply. PV will act as MPPT. Battery will supply, and grid. No need to do anything with the grid. No need to take power from the grid in this case. But if SOC is less than 60%, we need to have maintain some storage in the SOC or the charge in the storage so that it can be used in peak hours. We are talking here about the off peak hours. This is the off peak hour. C is for off peak hours. We want to have sufficient energy stored for peak hours. Therefore, if the storage SOC is less than 60%, then what we are going to do? PV will be acting as acting at MPPT, and it will charge the storage. And the grid supply and the PV. So grid plus PV will charge the battery plus supply the load. The net load is this now, battery plus the existing load. And this will be supplied together both by the grid and the PV, which is operating at MPPT. So PV at MPPT together with the grid will charge the battery as well as supply the load. Okay, this is done for off-peak hours. Now remaining is the peak hour. We were here. Is it a peak hour? No, we have already talked about off-peak hour. Now we go to the peak hour. Yes, it's a peak hour. Then what are we going to do? Now we need to check again the same thing. So this is the mode. Mode is already checked. Now we need to check whether the generation is more than the load. If the generation is not more than the load, that means load is more. Then we need to check SOC. If SOC is less than 30%, yes, then because it's a peak hour from the utility side, when we are talking about peak hour here, the utility is experiencing the peak. That's why this peak hour and off peak hour mode are concerned with only the grid connected mode. Because here we are talking about the peak of the utility, not the microgrid. That's why these two are for grid connected and this is for the islanded or isolated mode. Peak hour, the utility is experiencing the peak here. If the load is more than the PV generation, then we need to check the storage because we don't want to take anything from the grid. If the SOC is less than 30%, then we need to check again the same thing. If SOC is between 30 and 20%, then the grid will be disconnected. PV at MPPT battery will supply both essential and non-essential load. If SOC is between 20 and 10, then non-essential load will not be supplied, only essential load will be supplied. And if the SOC is less than 10%, then the battery will not be used. Here, only the essential load will be met by using the grid, supply from the grid, only the essential load. PV will be operating at MPPT and grid will only supply for the essential load. Because battery is already at 10% SOC, we cannot discharge it further. But if SOC is more than 30%, then battery will supply. We need not take anything from grid because it is already a peak hour. It's a peak hour. And SOC is more than 30%. Battery can discharge. PV at MPPT, battery can supply, grid is disconnected. Okay. Now, where are we here? This was the case when load was more than the generation. Now, if the generation is more than the load, then we need to check the storage. If SOC of storage is more than 70%, then excess generation battery will be disconnected and excess generation will be sent to the grid. Because it is a peak hour, we want to aid the grid. We want to support the grid. We want to support the grid. That's why if the storage, the energy stored is more than 30%, more than 70%, sorry, more than 70%, then PV is operating at MPPT and the excess generation over and above the load is fed back into the grid to support the grid. But if the SOC is less than 70%, then the battery will absorb. Excess generation from the PV will be used to charge the battery. Hence, meet the load because the generation is already more than what the load requires. And that is how this we see all these things are met here. We are able to reduce our reliance on the grid, especially during the peak hours. Just a minute. We are able to reduce our dependence on the grid, especially during the peak hours when the grid requires support. We are able to supply the grid. The DC microgrid is able to supply the grid during the peak hour when the storage is more than 70%. And it is supplying only the essential loads during the peak hours when the storage SOC goes below 10% because we cannot discharge, over discharge, deep discharge. we are able to cover both the grid connected islanded mode. We are able to reduce stress on the battery, and peak demand reduction is also happening here. All these things are being achieved here. Now the next topic was the design of smart grid and practical case studies. For performing this demonstration or hardware setup for this case study, for designing the test bed, many equipments are required and which are listed here. Seventy. Okay. RT first component is RTDS. We already know the full form. We have used this in previous week also. A real-time digital simulator. It's a hardware which have different numbers, many high power processing, pro- high high performance processors, which RISC based, FPGA based processors are there in RTDS, which are able to provide us a simulation at of in at a time step of even microseconds within in the same order. If we are, let's say we want to see some change, we want to see all the high frequency components in the order of 10 raised power 6 hertz. That means the time step required is of the order of microseconds. Even that the RTDS is able to do in real time. We need not wait for several minutes as happens in case of MATLAB, where the system size for a large system, let's say for a 432 node system in MATLAB, if we do a simulation at micro seconds time step, then it will take several minutes. But here, this real-time digital simulator is able to do the same thing within microseconds itself. It's it's very quick. That's why it is called real-time. It is emulating as if it's a real system. And that's why if we are able to do a hardware simulation considering RTDS, it is similar to as if we are operating in the real time. Here, this RTDS is a company which provide this RTDS. RTDS Technologies is a company which provides this real-time digital simulator, and a typical rack of RTDS can simulate a 72 node system, single phase nodes. That means if we are simulating a three-phase system, then it can only simulate a 24 bus three-phase system. One node for each phase. That's why for a three-phase, if the bus is a three-phase bus, then we need three nodes. That's why only 24 bus system. And if there are six racks, then we can have only 144 nodes. Not streams, like buses, 144 buses only. That's why you'd see in the lecture that the system of the Indian power system network, which was having how many total 575 buses and some 8116 lines. This was reduced to a 120 bus and 216 lines. Okay, which is less than 144. So we can simulate this system in the RTDS having a, if you have a 6 rack RTDS, then this system can be simulated. On 6 racks, which is there in IIT Roorkee, total a maximum of 144 bus system can be simulated at a time. Okay, so that's why uh, it's written here as 432 nodes. That's the limitation of the hardware. We can increase the number of racks to have a bigger, to simulate a bigger system, but it also adds to the cost. It's very costly. Then in RTDS there are different types of input and output format which are available, and there is this. These are the different uh, interfaces which allows the analog, the input. These are the input output peripherals. This is called as gigabit transceiver analog output, gigabit transceiver, gigabit, or let's say gigabit digital output, and similarly gigabit transceiver analog input and digital input. Both analog input output and digital input output are possible in RTDS. Then the next component is the power amplifier, which is a very important component when we want to do a hardware simulation, hardware in loop test, where we want to operate a motor, let's say. And since the controller is designed in the RTDS or Opel RT, which will provide an output of only up to 5 volts, but the motor requires 230 volts or 415 volts. If it's a 3-phase motor, then we need to amplify that 5-volt signal to 415 volts. For that, power amplifier would be required. But for testing a digital, let's say numerical relay or something, protection equipment, we don't require this power amplifier. If they need signal of up to 10 volts, then we can avoid this power amplifier and we can simply have 5 volts. We can boost it to 10 volts and then we can use it. Power amplifier is not required in that case. A smaller uh, boost to simple voltage boosting of twice order is sufficient here. That's why for operating the real equipments, power equipments, we require a power amplifier also. And it supports the power hardware in power hardware. Okay, so it can have, so it supports AC microgrid simulation up to 270 volts RMS in each phase. This is 270 volts RMS per phase. This is per phase. And it can also simulate a DC voltage up to 400 volts, DC microgrid up to 400 volts. It can provide zero lead, zero lag, and UPF also. All these things are possible. Then next is PV emulator, which is able to simulate, which is able to perform as if it's a PV plant. It's a PV power, uh, solar PV power plant. It can take in, it has this real world weather scenarios. It can also simulate the shading effects, and static and dynamic MPPT testing is also possible. Maximum power point tracking algorithm. There are several varieties of MPPT algorithms which are available, and we can test these different. And this PV emulator can help us model these different types of MPPT. We can select which algorithm we want to test. Okay, we can test these algorithms on this emulator. Whether, let's say, we have developed some new MPPT algorithm and now I want to test it, whether it's working as per desired as per our intended objective? Is it able to achieve that outcome? And we can also compare it with the existing MPPT algorithms which are available in the literature. Similarly, we also have a wind emulator. This PV emulator is a 1 kilowatt PV panel. There is one rooftop PV also, actual physical rooftop PV. This is operating 1 kilowatt. And this PV emulator, there are two PV emulator of 2 kilowatt each. Then there is a wind emulator, which is a DC motor driven doubly fed induction generator system, which is a type 3. You already know it's a type 3. Type 4 is permanent PMSG, permanent magnet synchronous generator. So this is type 3 wind turbine. And this also takes into account real wind simulations and also supports MPPT tracking. Then there is a physical diesel generator, a single phase push button based diesel generator is also there. It's a 3 kVA, 230 volts, 50 hertz, single phase operation. Then in storage, lead acid and a battery of 60 ampere hour and ultra capacitor of 58 farad is also available. Then loads, there is programmable load which can be programmed in all the three types: constant power, constant impedance, constant current mode. All these loads can be programmed and each load is 1500 watt. Total 4.5 kilowatt of load is there. Then converters, there are AC/DC and DC/DC converters, both unidirectional and bidirectional. Now we will move on to the hardware in loop experimentation. In hardware in loop experimentation, what happens is, first of all, it in this the hardwares are interfaced. We cannot use here Simulink. It will do offline studies. We want to see as soon as, let's say, as soon as I switch on the bulb in the bulb load, immediately there should be a change. I should be able to see the change in the motor speed. That sort of system is possible by doing this real-time operation. Okay. Now hardware, here the hardwares are interfaced with the real-time simulator. Hardware is interfaced with the real-time simulator, which contains the rest of the models. Here, the real-time simulator contains it can be the control algorithm, or if you want to check how interfacing this PV, let's say this is a PV plant, and how the integration of this PV plant in the distribution changes the power flow and everything. Then this here the real-time simulator will be having that distribution system network. System topology. And the control algorithm or optimization problem, whatever you want to do. That's why it offers a very cost-effective and safe method to test the physical devices under real-time operating conditions. First of all, it is cost-effective and also safe to test the physical device. Under real-time operating conditions. Okay. Now HIL can be of two types, open loop or closed loop. In open loop, there is only one way communication. Signals from the real-time digital simulator can go to the device. These are personal 5 volt. 0 to 5 volt signals. These are the signals which goes from in open loop. There is only one direction. It's unidirectional flow of. In closed loop, the loop is closed. Signals from RTDS go to the device and device also. The response of device is fed back to the RTDS. And this hardware in loop test can be of two types. Again, this is one distinction, one division, and another is control hardware in loop and power hardware in loop. In power hardware in loop, there is an exchange of power between the RTDS and the hardware setup, hardware device. So this we already discussed open loop. This is cost effective and safe to test physical devices. And hardware devices are interfaced to the real-time simulator here. In this also we have seen yes. In open loop, the signal from the real-time simulator are sent to the device. And in closed loop, the response of device is fed back to the real-time simulator. Now the hardware in loop which we were discussing, they are of two types. One is the control hardware in loop, one is the power hardware in loop. And control hardware in loop, the physical control or the protective relay devices, they are interfaced with the real-time simulator and they exchange analog or digital signals. The main important thing is they exchange signals here. Okay. They are not exchanging power, they are exchanging the analog or digital signals. And they exchange on the signals, they exchange the signals at low voltage levels, 10 volts. In power hardware loop, there is an exchange of power. They exchange power. Here, the real-time simulator is interfaced with a power device. This is very important here. This is interfacing a power device with the real-time simulator, such as motors, inverters, generators, transformers. Thus, they will exchange power. And that's why scaling is required to feed the amplifier. This is the uh, this is another representation. The same thing which we have discussed is shown in the form of a fluid diagram here. So this is our real-time simulation or simulator. From here, this is the first one. This one is the control hardware in loop, and this one is power hardware in loop. From the real-time simulation, we are taking signals out, whether it's uh, analog or digital. Then we need appropriate converters, digital to analog or analog to digital converters. Then we have an amplifier here. This is not a power amplifier. This will be a power amplifier. Okay, then the signal goes to these are the signals. They go to the device under test, and the output from the device under test also again goes to the real-time simulator. These are the signals we are directly sending these signals to the simulator. Now, our hardware in loop here, let's say we have a distribution system modeled here, model the real-time digital simulator, which is this RTDS. It uh, it has a hardware, right? We talked that there are 6 racks, and to run the system designed for designing the system, there is a software associated with this hardware, which is RSCAD. Okay, RSCAD. In that, we can, let's say uh, we have developed a distribution system. Okay, now we want to take the voltage signal out. Then, and the voltage here is, let's say, this is 230 volt single phase. Now the output of this RSCAD, this RTDS, whatever we model in the RSCAD, it runs. The hardware is this. The simulation runs on this hardware RTDS. RSCAD is this software, and the RTDS is the hardware. And the simulation will run on the hardware. And if you are taking the 230 volts voltage signal out, then the RTDS, the analog output is only between 0 to 5 volts. We need to scale this 230 volts between 0 to 5 volts. Scaling factor is required for that. So this scaling is here. Let's say this is a 230 volt signal. Now it becomes a 5 volt signal here. Then we convert this digital to analog converter. Then it goes to the power amplifier. Let's say this is the device under test, which is uh, any kind of, let's say this is a motor here. Then we need to convert this 5 volt to again 30 volts. Then this voltage and current sensors are used to sense the voltage and current. Then the sensor will convert this digital, their output is digital, and this will be converted into analog signal. We use some filters and then again feed it back to the real-time simulator. Here, because of this power amplifier, and this device is also power device. And for operating this power device, we require a power amplifier. Here, this device is not a power device. That's why we don't need a power amplifier. Yeah. Now let us move to this AC/DC distribution network, which was here we were talking initially, which I was talking about the power flow analysis. in case of transmission system and distribution system. And there is a lot of difference between transmission system and distribution system. Here, sorry, transmission, this is distribution. Now, what is here? Transmission system and distribution system. Now, let's say R by, let's say X by R. X by R ratio here is large. Small X by R ratio. It's a per phase. If it because inherent unbalance is there. Here detailed models are required for inverters. And components, if we talk about components, number of components. Here we require huge number of components like that. Even say loads, number of lines, number of transformers, everything. The number is very large here. Because in transmission system we club them, group the nodes together, group the loads together, and have an aggregate model. But here we have each and every load, different phases, different loads and balances there. And different types of loads are also there in transmission system. We consider load as constant power. But here, different types of loads are there. Zip is there, constant impedance, constant current, constant power. So many kinds of loads are available. Then for transformer, here in transmission system, transmission AC power flow, we are not worried about the detailed modeling of the transformers in terms of their phasor groups. Right? Whether it is star star, this is star star, star star ground, or delta star, or star delta, delta delta. We're not worried about this. We directly have an equivalent circuit for transformer. Just simply this, the simplest circuit. But here we need to model all these things. The three-phase model of transformer with all the interconnections. This the phase change, all these things are very important here. We need to model each and every detail here. That's why it becomes more involved, and the algorithms which we use for transmission system are no longer applicable for distribution system because of this X by R, because of the small X by R ratio in the distribution system, which result in convergence issues for the conventional Newton-Raphson in Gauss Seidel power Q. That's why we have modified Newton's method and forward, backward sweep and other types of methods are specifically designed for distribution system. And here the components that we see in the AC/DC distribution system is components are the loads, then we have generation, and this is distributed generation. Then we have different types of lines. We have buses, we have DC loads, we have EVs, electric vehicles, power panels, power converters. If we see this system here, this is all AC. Blue lines are in DC. Now this is AC here. We need to convert this AC into DC here to connect DC grid. DC microgrid. So this is the voltage source converter, which is converting the this AC into DC, and these are all DC buses. And here we have a DC-DC converter because it might be or these to this might be after this microgrid might be operating at a different voltage level, and this might be these voltages might be different. So here this is the AC system. This is also an AC system. Here we have a DC and the AC microgrid. This is the AC microgrid here. Small AC microgrid here, which has wind plant and what is this solar plant? This is PV plant. First we have a boost converter here. And then we have an inverter here. PV plant and wind farm are there. And as this is AC, this is DC, this all buses are AC loads. And then because we are connecting it at DC bus, we need to convert this AC into DC via voltage source converter. And then here we have DC-DC converter for integrating the DC microgrid. Now we talk about the different types of buses here. In AC buses, what are the three types of buses in AC power flow? In transmission system, any AC system, we talk about three types of buses when we do power flow analysis because we want to, if we talk about the equation, if we write the equation of P and Q, if we write the P and Q equation, then we will see that there are total number of variables are 4. One is P, Q, V, and delta. These are the 4 variables at each bus, but at each bus we have only 2 equations, one for power, one for reactive power, one for active power, relating these 4 variables. Now 4 variables, but only 2 equations, therefore we cannot solve it. That's why we need to specify half of the variables. That's why and it is in, this is as per our natural bifurcation also. We have a bus, a voltage controlled bus where the voltage is fixed, specified. The voltage is specified. These are the voltage controlled buses where voltage is specified. Voltage controlled buses here voltage is specified. There are PV buses where P and V both are specified. These are the generator buses. The generator generates at a specified power at a specified voltage. Voltage controlled buses can be the buses where capacitors are connected. Any reactive power compensation device is connected. Then load bus where P and Q are specified. We don't know delta and V here. No. Here we know the magnitude of voltage, but we don't know the delta, the angle. Angle is not known. We need to find delta and Q for the PV buses. And for the load buses, we need to find out delta and Q. Okay, then we need one bus to cover all the losses and also to provide a reference for the angles. That's why this bus is called a slack bus, and here V and delta are specified. The voltage is 1 angle 0. Yeah, these are the three types of buses in the AC system for AC. And for DC system, we have load buses where, because in DC frequency reactive power is not there, in DC will be having load buses where P is specified and we need to find out the voltage. And second types of buses will be the voltage control buses. Here P is specified and V is not. Here V is known. Voltage control bus, but P is not known. Okay. Now power flow solution of transmission system cannot be used because in transmission system there is a low R by X ratio. Distribution system, same thing. This we already discussed. Here distribution system is more complex. It has more number of elements. There are renewable generators, converters, and we need to model everything in detail. We need to model the transformers also, their connections in detail. Then here we need to model storage and DC loads also. Also need to take into account the control objectives of the converters. Different types of converters also need to be modeled. And then representing the operating state of combined AC and DC system. All these things are required here. Here the type of DC buses we already seen. In DC bus, one is DC load bus, which is the P bus. Net power, DC power from the load or DG inducted into the bus is known, while the DC bus voltage is not known. And the DC voltage controlled buses, here the voltage is known and power generated at the bus is unknown. These things we have already discussed. Okay. Then we discuss the AC-DC VSC converter model and DC-DC converter model. And their equations were there, you can go through that. Then one was the AC-DC, VSC based AC-DC converter model. And one was the DC-DC converter model. These two models. Here in DC-DC, the equations were given for the voltage, and in terms of, let's say this is the DC-DC converter here. DC converter. In here we have some voltage level, let's say V1, this is some V in and V out. And similarly, current is also I in and I out. So V in, V out is equals to V in into delta in case of a buck converter. And V naught is V in upon 1 minus delta in case of boost converter. And in buck boost converter, it is this. This is buck boost. Similar thing we can also write for the current relationship. There it will be this I naught is equals to delta into I. I in is equals to delta into I naught. This also we have seen AC, DC, VSC, DC, DC, and AC, DC converters. Modeling of these converters we have seen, and the equations are there in the AC/DC. This is DC/DC, AC/DC, LCC model. This is LCC model. This is VSC model. This is line commutated converter. Then distributed. These are converters. Then DG modeling. Next is DG modeling. This is a DG modeling here. Then here we have 4 types of DGs available: type 1, 2, and 3, and 4. Type 1 DGs are one which deliver active power only. For example, PV, solar PV, fuel cell, and they are integrated with the grid with the help of converters or inverters. Type 2 DGs are those which deliver both active and reactive. For example, the synchronous machines, cogeneration plants, or gas turbines. Then we have type 3, which deliver only Q. For example, is synchronous compensators, condensers, synchronous condensers. And they operate at 0 power factor. Type 4 are those which deliver power, active power, but consume very active power, and these are induction generators. So this is we can model these as PVDG. Bus, VDG, bus, PQDG, bus, and DG, E-type DG or bus. So this is type 1, this is type 2, this is type 3, and this is type. Okay. We have 4 types of DGs here: type 1, type 2, type 3, and type 4. So type 1 is one that delivers only active power. For example, PV and fuel cells. And then type 2 are those which deliver both P and Q, both active and reactive power. And this example are synchronous machines. Type 3, they deliver only reactive power. This becomes a P-type DG, or you can say P-type bus while modeling. Because we need to model them for doing the power flow or distribution system or even the AC-DC power flow analysis. If a DC microgrid is connected to the AC network, it will become an AC-DC power flow. And then type 2 is, we will call it as PQ type, because it is delivering both P and Q. It will be a PQ type bus or DG, you can say. This is delivering Q, this becomes a V type voltage regulation. Since it will be a voltage controlled bus, it will be a V type DG or bus. And last one is a PV type. Last one is PV type DG or bus. Okay, induction generator. And last topic which was discussed was this grid connected DC microgrid, and it's the hardware implementation. And we'll see this first. And this is the hardware setup for the DC microgrid connected with the grid. Connected. This is grid. This is for the grid connected mode. And same thing we can model as isolated grid also. That case, this grid emulator will be removed from here and we can have some load here instead of this grid emulator. This is a grid connected DC microgrid hardware implementation model. Here we see this is a grid emulator, and this the input of this grid emulator is the supply from the distribution system. This emulator is acting as if we have a grid here, which is giving us as infinite, acting as an infinite bus. We can take power from it. We can even inject power into the grid via this grid emulator. And this grid emulator has several functions. It can also act as a DC source while acting as an AC source. It is grid emulator. It can also act as a source of DC as a DC source or else as a battery. Can also emulate a PV source. And this is a point of common coupling, which in hardware is represented by the miniaturized circuit breaker MCB. And here we have these Hall effect based sensors for current and voltage sensing. For current, these are Hall effect based voltage and current sensors. Three-phase voltages and currents are sensed from here. And these are given as input to this control design, the current, because we want to control this converter here. Okay, this is AC side and this is the DC side. So here we have this DC AC converter. And this is the DC microgrid. Here we are, this is the DC microgrid and this is the power amplifier. Okay, so in DC microgrid, we have a PV plant and we have a storage here. We have some DC load also. And this is made in OpenRT. So this power amplifier is acting as a DC. This is emulating a DC microgrid here. And this, whatever system we are designing here, it is designed in the Opal RT, because the output of Opal RT will be only, it will be a, here we are taking out analog signals, and these will be voltage signals of 0 to, in the range of 0 to 5 volts. But here we are connecting everything to AC side, and this converter is operating at a higher voltage. We need to amplify these voltages. That's why we require power amplifier here. And because it's a bidirectional thing, we can have output from power amplifier back to the polarity also. We are having voltage output and current input here. Okay, this is a capacitor, and to have a power flow from DC to AC sides, this voltage of capacitor should be more than the peak voltage here. Okay, because we have this DC-AC converters, to perform the, to have achieve the desired control objective, we need to generate the appropriate pulses for each of these 6 converters, which are 6 switches which are there in the converter, these 6 switches. And for that, we are using this DSP based controller, digital signal processing based controller, is used to generate these pulses. And this controller, it requires these 3 voltages, 3 currents, 3 phase voltage, 3 phase current, and the this voltage across this capacitor, the DC link voltage, which is the DC link voltage. Was to have power flow, this bidirectional power flow, controlling this voltage is very important. That will determine how the power flows. If this voltage is higher, then the power will flow here in this direction, and otherwise it will flow in this direction. For that, we need to control the capacitor voltage, the DC link voltage. Okay, yeah, so this thing here is as is this control logic is implemented in the DSP controller here for generating the firing pulses. Or and here we are saying we are taking these three phase voltages, 3 phase voltages and 3 phase currents, and these are sinusoids. These are sinusoidal signals. These 3 phase voltages are sinusoids, and we cannot use our regular PI controller on sinusoids. Like these regular PI controllers, they work with DC signals. But if we want to have, we want to operate these, we want to control these sinusoids, then we need to have the PR, proportional plus resonant converter. Not control converter, proportional plus resonant controller. This is also a advanced version of PI controller. It's a PI controller only, but it is the word resonance. Resonance is coming based upon the resonant frequency of the higher order. The natural frequency of the, because this is a first order controller. This is a first order controller. We can see here Kp plus Ki by S. This is a first order, but PR controller is high order. It's a higher order. This is the most basic one, which is a second order converter, but it can be even third order and fourth order depending upon the system we want to control. It can be even higher order, and that's why its design becomes complicated for much higher orders. Here it is second order only sufficient. We are using PR controller. Otherwise, that's why first of all, if we use all the three signals and give it to PR controller, then we need to design three PR controllers, one for each phase. Okay, one for each phase. One for phase A, B, and C. To reduce one PR controller, what we are doing, we are converting this ABC voltage or current in ABC frame to alpha beta frame. Here you can see this one. This is reverse from alpha beta to ABC. But for this current A and B reference, these are generated by converting the first ABC to alpha beta frame. Now, if we want to use the same PI controller, then we need to convert the ABC into DQ frame. These DQ signals are in quadrature with each other and they are DC signals. If we use DQ, then we can use our normal PI controller. Here also will require only two PI controllers. In alpha beta also we require two PI controllers, but the PI controller will not work here. We will require higher order PR controllers. Once we generate the reference alpha beta current signals, we compare it with the actual signal which are derived. These alpha beta, this IAB, this IA and IB are coming from IABC when it passes through the transformation ABC to alpha beta. You will get I alpha and I beta. This I alpha and this this I beta are coming from here. Similarly, this voltages also we need to pass through UABC. We need to convert them into alpha beta domain first, and then you will get U alpha, U beta. And we compare these two, and then finally what we get, we convert again into ABC for the modulation. And this is the DC bus voltage control. Here we have the reference DC voltage. This is the actual DC voltage. Here we can use PDC because simple PI controller, because PDC is already a DC quantity. That's why you can see here we require a PI controller, but here we require PR controller because of these sinusoidal signals. I alpha and I beta are not DC signals, while VDC is a DC signal. That is the difference you can see here. PI and this is PR and this is PI. Okay, for tracking the frequency, we use the phase lock loop. Let's say the output of this is frequency. Okay. Let's move to questions now. Do we have any doubt? Okay. First question is the modes of power flow control strategy is or are. One is trough, off trough, isolated, grid connect. The correct options. We have already discussed the power flow control strategy for DC microgrid. In grid connected, we have peak hour and off peak hour mode. Then we have another mode is the isolated mode. So these are the two modes we have. Okay. One is grid connected and one is isolated. Second question is, in isolated mode of power flow control strategy, if PV is more than load, okay, first of all, it is isolated mode. No grid is available, that means. And PV is more than load. PV is more than load. This is the first, this is second, and third is the SOC is more than 90%. The SOC, the battery is already charged, and one of the objective or features of the power flow control strategy is to reduce the stress on the battery. And for that, we need to avoid overcharging and deep discharging. This we need to avoid SOC more than 90% and SOC less than 10%. This we have to avoid. And here it is saying that SOC is already more than 90%. That's why we cannot charge the battery further. And PV, since PV is already more than the load and it cannot be charged, and either it can be supplied to the grid because it is isolated mode. So no interaction with the grid here. Now, if PV will keep on generating more than the load, then there will not be generation demand balance, and it will result in instability. So we need to balance. That's why the PV in this case cannot, because it cannot supply to the grid. PV cannot supply to the grid here. Excess generation from PV or charge the battery. Both are not possible here in this case. Therefore, the PV has to operate at off MPPT. It cannot operate at maximum power point. And it will operate in bus regulation mode. Now we need to check the options. So A option is PV operates at MPPT. This is not correct, because if it keeps on operating at MPPT, then generation will be more than the load. And because storage cannot be charged and it cannot, even the excess generation cannot be fed back into the grid also, this option is not possible. Then load are met using conventional grid. It's already an isolated. The microgrid is an isolated mode. So load, this option is also not correct. And even because generation is already more than the load, why even if it is grid connected mode, we will not supply the load from the grid. Then battery supplies the load. Is this option correct? A battery can supply, but here battery will not supply because already the generation from PV is more than the load. The battery need not discharge. It can keep the charge intact for the grid for the future time when the generation is less than the load. PV operates at the off MPPT. This option is correct, which we were discussing. Okay, so this is same thing written here. In peak hour, the priority is not to take power from the grid. And even if we are supposed to forced to take power from the grid, then only supply the essential loads. So here the priority is either to supply the grid, support the grid when there is excess generation of PV and the storage is already also charged, then it can supply the grid, help the grid. So priority here is to supply the grid or support the grid or draw the minimum power which is required for only the essential loads in the grid interactive DC microgrid by ensuring that the DC voltage is within the limits. In off-peak hour, the conventional grid is able to deliver enough power at low cost. The battery can be charged. So charging of battery along with supplying load so that stored power can be utilized locally when the peak demand occurs. And in this case also the charging should be in such a way that this charging does not create a new peak demand during the off-peak hour. All this we need to take care. And in the isolated mode, or when the conventional grid encounters failure or outage, there will be isolation, and it is the DC microgrid is operated under extreme scenario when generation is less than the load with low SOC. In that case, there will be load shedding. And if generation is more than the load and SOC is more than 90%, which was the case which we were discussing, then the PV will operate at off MPPT. Okay. Two types of HIL simulation are two types of hardware in loop simulations: CHIL, PHIL, DHIL, all of the above. The two types are control hardware in loop CHIL and power hardware in loop PHIL. This is used when we want to interface test some power device from a real-time simulator. That's why here, since here power devices are involved, power amplifier is required here. And here the signals are, so here power is exchanged between the real-time simulator and the power device. Here control signals are, here signals are exchanged up to 10 volts between the device under test and the real-time simulator. DC microgrid functionalities are stability, margin, flexibility, grid support, service. So all of these are service. It can support the grid, capability to provide ancillary services. It has sufficient stability margin in steady state and transient operation mode. Then in flexibility, you can say there is possibility of reconfiguring the system online during faults by disconnecting from the utility grid. And scalability, there is a possibility to seamlessly add or remove power units. These are different types of functions which are available and go through. In a typical DC microgrid, which of the following is not a mode of operation? Grid connected, islanded, autonomous, or none of the above. So none of the above is the option. Which diagram is not? Yeah, here is the diagram. You will see that. Okay. Select the correct option for the control layers in DC microgrid. 0 first, second, third, 0 primary, secondary, tertiary, 0 first, middle, last, none of the above. So both these two questions are related. We'll see in the next slide. Explanation for these two questions. So here the correct option is 0 primary, secondary and tertiary. We can see here the question for the modes of operation of DC microgrid. Here if you see we have these two switches SW1 and SW2. When both the switches, this switch and this switch, when both the switches are connected, closed, SW1, SW2 are closed, then it's a grid connected mode. When SW1 is closed and SW2 is open, it is islanded mode. So this is open. Now only this grid is there. So it's islanded mode. And when SW1 is open and SW2 is open or closed, then it becomes an autonomous mode. Same thing is written here also. Grid tied, islanded, and autonomous. The difference between islanded and autonomous is that here it serves DC in islanded mode when SW2 is open and SW1 is closed. It is serving DC loads which are connected to DC bus, AC loads connected to AC bus, and this PCC load also. And this is closed SW1 and SW2 is open. But when SW1 is open, then PCC load are not served by the DC microgrid. That is the difference between the islanded and the autonomous mode here. And you can see the control layers are, these are the control layers. Zero level is the control of grid tied inverters and variables, which is very fast on the order of milliseconds. Then primary is automatic load sharing and grid support. Secondary is microgrid synchronization. And tertiary is optimization, power flow control. From this is fast to slow. The next question is which of the following is or are correct about the DC microgrid? First, it consists of only DC bus. DC buses for interfacing DC sources and DC loads. Operates in 3 modes. Serves critical loads during grid outages. So which one is the correct option? Consists of only DC bus. This is not correct. And DC bus is for interfacing DC sources and load. Yeah, this is correct. Operates in 3 modes and serves critical loads during grid outages. The last 3 options are correct. Type 1 DG, this also we have already seen. What is the type 1 DG? That it delivers only P. Select the correct statement about AC-DC power flow. Newton reduction is the best method. It's applicable for transmission system, not for distribution system. There are 4 types of AC buses and 3 types of DC buses. There are 3 types of AC buses and 2 types of DC buses. Converter modeling is not an essential requirement. This is also not correct. Converter modeling is required. So all the options are incorrect here. Newton Raphson is not for this AC/DC distribution system. Okay. Do you have any doubt? Okay, so we are done for today then. Thank you for joining. We will meet for the last online session next Monday from 6 to 8 p.m. Thank you.